Good day, grade 12 learners. Welcome to today's technical science lesson. My name is Musa Zulu. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Right, as we have said, today we're doing technical science, and our knowledge area for today is mechanics. Our topics will be Newton's laws. Specifically, we'll be doing Newton's first law and Newton's second law of motion. Right, but before we can talk about the laws, we have to look at the structure of the paper that we are talking about today. Mechanics is a topic that is assessed in paper 1 in technical science. So paper 1 structure looks something like this, creators. You have two sections, section A and section B, where section A consists of 10 multiple choice questions out of 20 marks. However, sometimes you find that section A will also have matching items, which will be matching column A and B, which will be sometimes out of 8 marks. However, most of the time it will be just 10 multiple choice questions. Section B is structured or long questions that will be adding up to 130 marks. But if you do have the matching items on section A there for 8 marks, then it means section B will then be totaling 122 marks. Your grand total for the paper is 150, and the duration for paper 1 is 3 hours. Right, the contents and the topics and their weightings and marks are structured this way. The contents of paper 1, the knowledge areas there are 3. We have to do mechanics, which has about 93 marks in a question paper, weighing 62% of the paper. Then you also have electricity and magnetism, which has about plus or minus 33 marks in a question paper, weighing 22% of the whole paper. Then you have wave, sounds, and light, having about 24 marks in the paper, weighing 16. Again, the grand total, 150 marks, and the duration is 3 hours. Right, for today, our focus formula, or the formula that we're going to be focusing on, is the formulas for the forces, right? Specifically today, we'll be looking at this formula here. The F net is equals to MA. This is the formula that we are going to be looking at mostly for today's lesson, right? However, we need to be familiar with this formula here that we did, or these 3 formulas that we did in our previous grade. Starting with this one, F max S is equals to mu S N. And then with this one, Fk is equals to mu Kn. These are the formulas to calculate frictional forces. If you remember last year in grade 11, you learned how to calculate the frictional force, static frictional force, and also kinetic frictional force, where the S stands for the static frictional force and the K here is for the kinetic frictional force. In grade 10, you also learned about how to calculate the force of gravity or the weight of an object using the formula mg, where the m is the mass of the object and the g is the gravitational acceleration of the object. So you will need to know those formulas. These are the formulas that will come into play as you deal with a lot of problem solving when it comes to the Newton's laws. However, for today, we're going to be focusing on introducing this formula that you have never seen, that you are encountering for the first time in grade 12. F net is equals to MA. Right, before I go to the laws, Newton's first law of motion, I cannot talk about Newton's first law of motion without talking about inertia first. We have to talk about inertia, what it is and what it means, and try to explain inertia in details. This is going to help us understand what Newton is saying in his first law of motion. So, the first thing that we must be able to do, grade 12, like always, we must be able to define. We should be able to define inertia. And how do we define inertia? We define inertia as the property of a body to resist any change in its states of motion or rest, right? Now, if you listen to that statement, it's sort of like a general statement. But I find with inertia is that it's really something that is not difficult. It's general. All we are saying is that objects have a certain property or a tendency. They have a tendency, right? They have a tendency to resist change in their state So what does this mean? If I have a box resting or books resting on top of the table, right? These books are always going to resist to change, right? It means I'm expecting that these books, if I leave them here, I should always find them here. They are going to resist. It talks about the difficulty of moving. For me to be able to move the books, I have to exert some form of force. They cannot just move on their own. They have to be moved by something or someone. So they will always resist their state of rest. And it also says, once an object is moving, once an object is in motion, the object wants to stay in that linear motion. The object does not want to stop. The object does not want to change direction. It just simply wants to stay in that motion. For me to stop that object moving, for me to stop that object's motion, I have to apply or exert a certain amount of force. So all objects tend to do that, and to me that's normal. Once an object, if you roll something down a steep surface, it always wants to continue rolling down until something stops it. So that's what inertia is. It is the tendency. All objects have this property. All objects have this property. They have a property to stay in their position, stay at rest if they were at rest. And they also want to stay in motion once they had started moving. The only thing that can change that is some external force coming into them. So that's what inertia is saying, right? I have some examples here that I want us to look at. If you look at if maybe you can have an object, right, and a cup, as you can see there in that diagram, and you rest an object on top of a flat surface, right? If you are able to move this flat surface quick enough, you would notice that as you push this quick surface, the object on top, say maybe you are putting a coin in there, that coin on top, what it's going to do is it will fall directly inside the cup. Why is the coin falling directly inside the cup? It's because the coin is resisting to change its state. The coin was resting on top of that flat surface. It wants to continue resting. It does not want to move. That's why it is not moving with the what? With the surface, the flat surface, as you are pushing it out of the way. So the coin wants to resist. It wants to stay at rest. That's why it remains in that position, then eventually falling into the glass. Inertia is also the reason why, if I'm sure most of us have felt it, you are in a car and the car is moving, and then the driver of the car somehow has to stop immediately, meaning maybe hit a dead brake or something like that, has to have a sudden stop. Whenever that happens, you would notice that you inside the car as a passenger, you tend to move forward where the car was moving initially. So what is happening? What's causing this motion? What's causing you to move forward when the car has stopped? It is inertia. It is your inertia. You are an object and you are resisting to change your state of motion. So when the car was moving, you were also moving with the car at the same speed or same velocity. So if the car comes to a stop, it is the car that is coming to a stop. The forces have been exerted on the car, but not you inside the car. So what do? You resist to change your state of motion. You continue moving forward. That's why you are going to jerk forward until you try and fight it yourself to stop yourself from doing that. So you jerk forward like this because of inertia. You are resisting to change your state of motion. You were already in motion, so you continue in that motion. This does not only happen when the car is moving forward, but sometimes you'll find that this happens if the car is starting, right? An easier example is if you have ever been in a train. If you've ever been in a train, like this lady here is in a train and she's holding a handle there of the train. And then the train is not moving at first, right? Then suddenly the train starts to accelerate forward. When the train starts to accelerate forward, and again, I'm sure most of you would recognize this, when it happens, what tends to happen is that the person inside the car, train, or whatever they are inside, they tend to move backwards, right? So the question is, why are you moving backwards? Why are you moving backwards while the car is moving forward or the train is moving forward? You are moving backwards again because of your inertia. Your inertia, it is your property, it's the tendency of this object that is you to resist. So your body is resisting to change the state of rest that you were in. So when the train was not moving, you and the train were at rest, so stationary. Then the train starts moving. When the train moves, your body resists to move. It does not want to change its state of what? Of motion or rest. So it resists to move, therefore it falls backward. But because your feet or the feet of this lady are in contact with the train drags the feet along with it as it moves. That's why you find that when you fall back, only your upper body falls back, not your whole body. If you are standing, you will notice that the only thing that falls back is your upper body. That's the part of the body that is not in contact with the train. The legs and the lower body are in contact with the train, so the train is dragging them with it as it moves. But your upper body is not being dragged. Therefore, the upper body does what? It resists to change its state of rest. It wants to remain in the position that it was in. So basically, that's what inertia is. It's just the resistance of an object to change its state of rest or motion. It wants to remain where it was. If it was stationary, the object wants to remain stationary. If the object was moving, then the object wants to continue moving as it was without being stopped. So these are the reasons why you would have those jerking motions if the car is either suddenly coming to a stop or the car is suddenly starting to accelerate because of the inertia. Right. Another part of inertia that I feel like is general information. This is why I was saying these things to me are not that much groundbreaking or difficult to understand, because this is general. If we look at the relationship between inertia and the mass of an object, anyone after this thing has been explained to them will say, well, I've seen this in my real life, right? What is the relationship between inertia and mass? The relationship is that inertia is proportional to mass, right? Inertia is proportional to the mass of the object. What does that mean? If you've seen, if I have just a small box on top of a table, I can easily push it away, right? You can easily push, or let me make an example of in your house. You have a chair, and then you have cut a wardrobe, for example. It's easy for you to move a chair out of the way, but it is difficult for you to push the wardrobe because the wardrobe is big, the wardrobe has a larger mass. So if something has a greater mass, like this object here, it's going to have what? Greater inertia. It will resist to change more. Remember, inertia is the property of a body to resist any change to its state of motion or rest. So when something has a greater mass, it's going to resist to change more. It will be difficult for you to push that wardrobe out of the way because of its mass. It has a greater mass. So if the mass is more, right, the inertia is also going to be more. So we are going to have high inertia because of high mass. But if the mass is less, like in this case, you have less mass here, you are also going to experience less inertia. So it means the resistance of this small mass here is going to be small compared to the resistance of this big mass. It would be simple to move this, something that you can just simply move without even noticing, without exerting that much, that big of a force. But for the other one, you have to exert a bigger force. It is because of their inertia. So that gives us a relationship between the mass and the inertia. To say, if I have a greater mass, I am going to have a greater inertia. But if I have a lesser mass, I'm going to have a lesser inertia. Another example that is coming to mind is, think of a ball. It is very, very simple to stop a ball. Someone passes you a ball and then it's coming directly to you, right? A ball is something that has extremely small mass, right? You can stop it. You use your hand, you use your feet, you use whatever you want to use, but you can stop it and it's easy. Now take that ball, this ball, and compare it to a car, for example, right? What's the difference between these two things? Mostly it's the mass. Their mass are not the same. This one is going to have big mass, this one is going to have small mass, right? Easy to stop this one from moving. Remember, inertia, the property of a body to resist any change in its state of motion or rest. So these objects were already moving. Let's say these objects are already moving. The ball is already moving, coming towards you. Your job is to change its state of motion by stopping it, right? So it resists that much. The resistance of the ball is very small. It's easier for you to just stop the ball. However, it's not going to be as easy to stop the car. It's in fact dangerous. You stop a car, a moving car, that's very dangerous because it's not even easier to do that. You might even get yourself hurt there by trying to do that. So the mass of the car is high. That's why it's difficult to what? To stop the car. So if the mass is high, it means the car is going to have what? High inertia. So it's going to resist more to change its state of motion. It's going to fight you more from stopping it. Objects do not want to change their state of motion. They tend to what? They tend to resist that. They don't want to change their state of motion. They do not want to change from rest to moving. They don't want to change from moving to resting. So they don't want to do that. So the bigger the mass of the object, the greater the resistance, the greater the difficulty of stopping it from moving or from starting it to move. Because even if you think about it, even if these ones were at rest, initially they were not moving. You wanted to move them. It's easier to move a ball. It's very, very easy to move a ball, but it is difficult to push a car. It's difficult to push a car. Most of us, we cannot push a car on our own. We need help from other people to start pushing a car. So it's very, very difficult. What's causing the difficulty? It's the inertia of this object. What's causing this one to be easier? It's the inertia. Its inertia is small. And what's causing its inertia to be small? It's its mass. So the smaller the mass, the smaller the inertia. And the greater the mass, the greater the inertia. That's why we are saying the relationship between inertia and mass is proportional. So if one they are increasing, they both increase. If the other one is decreasing, the other one also decreases. They have a proportional relationship. An increase in the mass will increase the inertia. A decrease in the mass will decrease the inertia. So the inertia then tells us that the inertia depends on the mass. If that is the case, then it means we can then come up with a definition of mass from inertia, because it is clear to us that we can measure the inertia using the mass. So by looking at the mass, or by getting the mass of an object, I can be able to tell how big or how small the inertia of the object is. By looking, if the object is small, then immediately I know that the inertia of that object is going to be small. If the object's mass is big, immediately I know that the inertia of that object is also going to be big, right? Therefore, I can come up with a definition that is going to define mass, and I can say, I know that this mass measures the inertia of the body. Therefore, its definition is mass is the measure of the inertia of a body. It measures the inertia of the body. So these are the definitions I want you to know. I want you to know the definition of inertia is the property of an object to resist any change in its state of motion or rest. And I also want you to define mass as the measure of the inertia of the body. And then from there, I want you to know the relationship between the two. I want you to know the relationship between the mass and the inertia. That mass is directly proportional. Mass is proportional to the inertia, right? The bigger the mass, the bigger the inertia. Okay. Then after that, that can take us now to Newton's first law of motion. Because if you look at Newton's first law of motion, you would realize that Newton's first law of motion is a detailed explanation of what we've just talked about, inertia. So just Newton's first law of motion just gives a clear indication or a clear details as to how inertia is actually working. But it is also talking about objects not changing their state. But let's take Newton's first law of motion. It says an object continues in a state of rest. That's the first part. An object continues in a state of rest or uniform velocity unless it is acted upon by a net or resultant force. That's where the great detail in Newton's first law comes in. The unless part, it gives details, it gives more details of this inertia, because if you look at the first part, this first part says almost similar thing as inertia. That's why sometimes Newton's first law is even referred to as the law of inertia, because they are very, very closely similar. An object continues in a state of rest. The same thing, an object resists to change its state of rest. So if it resists to change, then it will continue in a state of rest or uniform velocity. So that means the object will continue moving with the same speed, with constant velocity, right? It will not change its velocity. It wants to do that, right? However, the Newton gave a detail here to say that only happens unless it is acted upon by a net or resultant force, because in reality we know that objects can be moved from one place to another, right? Yes, they are resisting. Yes, those books on top of the table are resisting to change that, but in reality they can't be changed, right? So that's where the clarity came in with Newton's first law of motion to say, yes, it will resist, but it will resist unless it is acted upon by what? A net force, in this case, which would be changing its position, moving it from rest. Or if the object was already moving, right, there can come a net force that is going to do what? Stop it from moving. So that's why the part is there to say unless. So the object will continue in a state of rest or uniform velocity, but this will happen unless it is acted upon by a net force. So the expectation is that if I take something and I put it on top of the table and I leave it, I expect to come back and find it here. If I don't find it here, what does that tell me? It tells me that there was a net force that acted on it and moved it from where it was, right? If I had something that was moving, right, and it was moving, the expectation is that this thing should continue moving forever and ever. However, that will only happen if there is no net force that will act on it. So that's why the part there that says unless it is acted upon by a net or resultant force. So it will continue, right? I also have a demonstration here that shows that here's the ball here, and this ball, the expectation is that it will remain at rest, right? The ball will remain at rest unless it is acted upon by a net force. The second part of my picture here shows a net force acting on a ball in the form of a player kicking the ball, right? When the player starts kicking this ball, he's exerting a net force. Then after exerting a net force on the ball, then the ball will change its state. It's no longer continuing in a state of rest. It now starts doing what? Moving. So it changed because there was a net force that acted on it. An object continues in a state of rest or uniform velocity unless it is acted upon by a net force. Now, once the object has been kicked by the player and then it starts moving in this direction, the expectation is that, according to Newton's first law of motion, this object should then now continue moving forever. It should continue moving with the same speed forever. An object in motion will continue with constant speed and direction. It does not change the speed, it does not change the direction, forever moving in its original direction. However, again, Newton gave us this clarity here to say this will only happen unless there is a net force that acts on the object. As you can see here, this ball is being kicked. It moves in this direction, right? It goes into the pole, and then it finds a net. This net will then act as a what? As the net force. It acts as a net force that is going to what? Stop the ball from moving. So the ball is no longer going to move forever and ever, because there now is a what? A net force, or sometimes referred to as a what? An unbalanced force, an external force that comes from a different place. So Newton was actually clarifying inertia there to say an object continues in a state of rest or uniform moving with constant velocity unless it is acted upon by a net force. It is very, very important that you know this law, as it is very important to know the first definitions, the definition of inertia and the definition of mass. It is important that you are able to state this law. These are laws that are mostly asked in your final exam, grade 12. So you must be able to state it. And when you state this law, it's important to state this law in this manner, because these definitions and these laws that I'm giving you are coming from your examination guideline, which should be your number one tool when it comes to definitions and stating of laws, and also your formulas and all those things. You use your exam guideline. You don't want to define according to your own understanding. You want to define according to the examination guideline. And the examination guideline gives the law in this manner. An object continues in a state of rest or uniform velocity unless it is acted upon by a net or resultant force. Right? So, why do we need to know this? Why do we need to know these Newton's laws? As we've said, this is almost general. It's true. When an object is at rest, it will remain there. And then if someone starts moving it, well, they've exerted an external force. Why should we know this? Well, this can come in handy in our life, right? I want us to imagine using the first diagram here. If you are riding this bicycle, let's say this was you, riding this bicycle in this direction, right? Bicycle in this direction. Let's say this bicycle is moving at a velocity of 5 meters per second, right? If the bicycle is moving at a velocity of 5 meters per second, it means you are also moving at the same velocity as the bicycle. It is in the same direction, right? So, if it so happens that somehow there is a barrier that the bicycle comes into contact with, what is going to happen is that that barrier will stop the bicycle from moving, right? And as we said, again, from inertia, your body will resist to change its state of what? Of rest. And according to Newton's first law of motion, you will continue moving with what? The uniform velocity. So it means you will continue moving 5 meters per second in the original direction. But remember, the bicycle has done what? Has stopped. What is this going to cause? This is going to cause you to fall, and you are going to fall forward. You are falling forward because you are continuing to move in uniform velocity. So the net force only acted on the bicycle, the net force that stopped the bicycle, it only acted on the bicycle, not on you. So you continue moving with the constant velocity. So this is dangerous. It might not seem so much dangerous when you're in a bicycle because you fall and you pick yourself up. However, when we go to the second scenario, then you will see how dangerous it can be, right? Because now, if you are in a car, right, it's a different story altogether. A car is not covering a small amount of velocity. Cars will be covering 120 kilometers per hour, right? That's a large amount of velocity that the car is moving at there. So let's say here's the car moving with a velocity of 120 kilometers per hour east, maybe, right? If you look here in these two scenarios, in scenario one, we have a lady there driving a car, and the lady is not wearing a seat belt, right? So if the lady is not wearing a seat belt, moving at 120 kilometers per hour, if it so happened, as it has happened here in scenario 2, that the car suddenly comes to a stop, maybe the car crashes into a wall, into a pole, or into another car, but it suddenly comes to a stop, it will be the car that comes to a stop. And remember, both the lady and the car are moving with the same speed. So if the car was moving 120 kilometers per hour, then it means the lady inside is also moving 120 kilometers per hour. If the car happens to come to a sudden stop, what's going to happen? The lady will continue moving with that 120 kilometers per hour. According to Newton's first law of motion, an object continues in a state of rest or uniform velocity unless it is acted upon by a net force. So the lady will continue moving in that speed of 120 kilometers per hour. So in this case, she will continue unless she is acted upon by a net force. So what is going to be the net force that is going to act on her? It will either be the steering wheel, it can be the dashboard, and she can also go through the windshield, as it is shown here in the diagram. Here's a picture of the lady going through the windshield. Now this is much more dangerous than the first scenario, because here you can fall and pick yourself up. Here, this accident could be fatal, and most of the accidents where people are not wearing their seat belts are fatal. When the people are going through the windshield, a lot can happen there while you're going through the windshield, and again depending also on the speed of the car. But if you're not wearing a seat belt, it's very, very unsafe, so it can be a fatal injury there, and you can end up losing your life. However, if you look at the second scenario, the seat belt comes in now. So a seat belt is a very, very important tool in cars that was there because of Newton's first law of motion. Knowing that when you are in a car moving at a certain speed, the car is moving at a certain speed, you are also moving at that speed. So if we have that knowledge, then we know that if a car comes to a stop, you will continue moving. So what can we do to try and avoid these fatal injuries? What can we do to stop ourselves from continuing to move? We can introduce a tool like a seat belt. Put in a seat belt around your car so that, or around your seat, so that if it happens that the car suddenly comes to a stop, as you can see here, let's say she was still moving with the same speed of 120 kilometers per hour. As you can see here again, she comes into a sudden stop, maybe crashing there. But as you can see, as she is going forward, what happens? The seatbelt comes in and stops her from going forward. So in this case, instead of the dashboard, the steering wheel, or the windshield acting as a net force, the seatbelt will come in and act as a net force before she can get to things that could be potentially harmful to her. So seatbelts become important, and seatbelts are now here, and as we can see, they were here and they were formed because of Newton's first law. These accidents are so much fatal that it even became a law to say all cars must have seatbelts in them. And the reasoning behind that is Newton's first law. The reasoning behind that is that people, if they are moving in a car at a certain speed, or the car is moving at a certain speed, they are also moving with that speed. If the car suddenly comes to a stop, they are going to continue moving and they crash out. These are not just stories that I'm telling you, grade 12. These are questions, these are potential questions that you are going to encounter in your final exam, where they are going to give you a scenario and they will ask you to explain, according to Newton's first law of motion, why is the object continuing to move? I need you to realize that at first the object and the car, if maybe it's a car, for example, they are moving at the same speed. And if the car comes to a stop, the object inside the car does what? Continues moving in the original speed, according to Newton's first law of motion. I need you to have that in your mind. These are potential questions, not just stories that I want to share with you. So that's Newton's first law of motion, and that's what it's all about. It's about you being able to state the law, it's about you being able to understand the law, and it's about you being able to use the law to explain certain scientific scenarios. It's very important that you are able to state it, and it's very important that you are able to comprehend and understand the law so that you can use it for explanation. Right, now I want to go and touch on Newton's second law of motion. Okay, but again, like Newton's first law, I cannot touch Newton's second law of motion without starting by doing a small revision on acceleration. We have to do a small revision on acceleration. Acceleration was a concept that was done in grade 10, and we defined that acceleration in grade 10 as the acceleration as the rate of change of velocity, saying to ourselves that for us to say something is accelerated, it must change its velocity. I always say to people, think about the pedal in a car that is called the accelerator. If you press the pedal in a car, you watch the speedometer, it changes. So that's why it's called the accelerator, because its job is to change the acceleration or the velocity of the car, right? So that's its job. It changes the acceleration of the car. Therefore, acceleration becomes the what? The rate of change. So the velocity must change over the time. Mathematically, acceleration is represented by the formula A is equals to delta V over delta T, where A is what? Is the acceleration, right? And V is the velocity, but specifically the change in velocity, how the velocity was initially and how the velocity is finally, right? And T is the change in time. And T is the change in time, because we are looking at how the velocity is changing with regards to time. And if you remember that we also discussed in grade 10 that the SI unit for acceleration is meters per second squared. Another extremely important in grade 12, SI units. Right? It is important that we do not forget SI units. In whatever calculation or whatever concept we are talking about, we must understand the SI unit of that particular concept. Right. So I want to take a small example just for reminding ourselves as to how we're doing calculations of acceleration. An example like this one. You have a car of mass 2,000 kilograms, and we are being told that the car accelerates from rest. So it means the car changes its velocity. Once they say accelerate from rest, that tells us the car changes its velocity from rest. And the word rest, if you remember, it means that it's stationary. It means it has a 0 meters per second velocity. So it accelerates from 0 to a velocity of 25 meters per second, and all of this happens in 5 seconds. That's why we're saying it's the rate of change of velocity happening over time. Right, and we're being asked to calculate the acceleration of the car here. And how do we go about doing such? You always go and what? Look for the correct formula. In this case, the correct formula is going to be A is equals to delta V over delta T. So A is equals to delta V over delta T, right? But this delta V over delta T can be expanded, because remember, this is a change in velocity. So it means, if you remember, we expanded and we say it's Vf minus Vi all over delta T, right? Then you go to your statement and you look for your given. Do I have the final velocity? Yes, I do, because they say it starts from rest and then it goes to what? To 25. So I have the final velocity of 25 minus, do I have the initial velocity? Initially, it was moving at 0 meters. So basically not moving at all. So it had a velocity of 0 meters per second. And how long did it take for this car to change its velocity from 0 to 25? It took about 5 seconds. So our change in time is 5 seconds. So if you do the maths there, you are going to have 25 over 5. You should get that your acceleration is what? Is 5. And then this, the SI unit, meters per second squared, followed by the direction, in the direction of motion, or the original direction, right? It is important that when you are dealing with vectors, if you remember again in grade 10, we spoke about vectors and scalars. A vector is a physical quantity that has magnitude and direction. Extremely important that when we are answering questions based on vectors, I'm expecting that there must be a magnitude, and there must be an SI unit, and there must also be direction. You can't just say 5 and leave it like that. You can't say 5 meters per second squared and leave it like that. It must be 5 meters per second squared in the direction of motion. So that's just a small reminder of acceleration, because when we go and talk about Newton's second law, we have to remember what acceleration is. When we deal with Newton's second law, we have to remember what acceleration is from the lower grade, grade 10. Okay, here's another thing that I cannot talk about Newton's second law without touching on. Again, coming from grade 10, a little bit in grade 12, and in grade 11, and then very, very important in grade 12, the drawing of free body diagrams and force diagrams. It's important that we are able to draw correct free body diagrams and force diagrams. If you can't draw correct free body diagrams and force diagrams, you are not going to be able to solve problems related to Newton's second law of motion. You are going to struggle a lot to solve these questions if you cannot draw. So what I'm going to do here, I'm going to go over some examples that maybe you might have encountered before, and we are going to draw both the free body and the force diagram, reminding each other of how do we draw the free body diagram, how do we draw the force diagram of each. Right, so I'll start with the diagram here, one, right, and let's say the question says to us, draw a free body diagram indicating all the forces, right? One thing we must know is that free body diagrams we use a dot to draw them. We start with a dot, and we also use arrows. And after drawing that dot and arrows, we must always label our free body diagram. So we're going to start, when we're drawing a free body diagram, where do we start? I always say you start with the big dot. Let it be a dot and let it be big and clear. So here's our dot there, and then we start drawing the forces. If you remember in grade 10, we say for free body diagram, forces always start from the dot and they point away from the dot. They always point away. We never have a situation where the force is pointing towards the dot in a free body diagram. So let's draw those forces. So we have to identify the number of forces in this scenario. And if you look at this scenario, it should be having 4 forces. What is the force number 1? Force number 1 is the normal force. It is that force that is exerted by the surface and is perpendicular to the surface. And then the force number 2 is the force of gravity. The force of gravity is that force that is exerted by the center of Earth on the center of the object. And what is force number 3? Force number 3 should be the force that is applied, and force number 4 will then be the frictional force. You will notice something. Every time I draw the arrow, I label. Every time I draw the arrow, I label. Every time I draw the arrow, I label. Why am I doing that? I draw a line, arrow, label. I'm avoiding the issue of forgetting, because if you draw all arrows first and then think you are going to label after, chances of forgetting the labeling are high. You are going to forget to label. So don't do that, grade 12. Immediately you start with a dot. The moment you draw each force, label it. Each force, label it. You are not going to forget. If you want to draw the whole thing, you are going to forget. And also, if you do this, if you draw this cross thing, right, and then you have a dot and draw a cross and think to yourself, I'll put arrows after, again, you are going to forget one of those arrows. And it's very, very unfortunate, because you are losing marks if you do that. So each time you draw the arrow, the line, or the force, put the line, put an arrowhead, and label it immediately. Go to the next one. Arrow, label. Arrow, label. That way you avoid making mistakes. So this will be a free body diagram that indicates all the forces that are acting on this object. Okay, what about the force diagram? If you remember the force diagram, we said this one must be simplified into a small box. It's not a dot, but it's a box. And how do we draw the forces there? Well, we already know how many forces are there. We have 4 forces, but we must be careful here. Forces here do not start from the same place, like here where they start from the center. So you can't be having forces starting all over the place here. Forces are starting exactly where they are being exerted in a force diagram. For example, if we look at the normal force must start from the surface. Why? It is the force exerted by the surface perpendicular to the surface. And if I am drawing the force of gravity, I expect to see it starting from the center of the object. It must not start here underneath the object. It must start from the center, indicating that it is the force that is exerted by the center of the Earth on the center of the object. Then the force applied can start wherever it is being exerted. In this case, it's being exerted here. Then this is going to be your force applied. And the frictional force, again, is a force of a surface. So when you draw your frictional force, it must be exerted on the surface or drawn on the surface here, covering the whole surface of the box with its arrow and its label. So that's how you draw frictional force diagrams and free body diagrams. Grade 12. Right. So we're then going to go to the next one and draw a free body diagram and see how to draw a free body diagram there. The free body diagram for this one will look something like this. You will have a normal force, you will have a force of gravity, and then you will have a force applied at an angle, and then you should have a frictional force. Same thing here for the force diagram. You will have your normal force starting from the surface. You will have the force of gravity starting from the center. You will have the force applied at an angle. Then you will have the frictional force. So this is how you draw force diagrams. Let's look at two other examples, and then we can continue and start Newton's second law of motion. Okay, here again for the free body diagram, we will have our normal force. We will have our force of gravity. Then this time around, the force applied should be facing in this direction. Why? Because it cannot face the dot. So it should be facing away from the dot at all times. Then you are going to have the frictional force. Right. This one over here, I will do only one. This one, and then I'm going to leave this one for you to do. I will only do this one because this one has tension. If we call this a string, there's going to be tension. So the free body diagram here will look something like this. We'll have a normal force, we'll have a force of gravity, and then this time around you are going to have tension, and then here you are going to have the frictional force. The force diagram there will be similar. We're going to have the normal force starting from the surface. You are going to have the force of gravity. You are going to have tension, and you are going to have frictional force. Simple. So what I want you to do, I want you to draw the free body diagram here, and I want you to draw the force diagram here on your own and see if you are able to do that. You should find that it is 5 forces that are here, right? So for free body diagram, I'm expecting 5 forces, and for the force diagram, I'm also expecting 5 forces. And one thing that we should remember about free body diagram and force diagrams is the marks in the exam. If I'm asking this one, I will give it 4 marks, right? The marks are allocated according to the number of forces that are there in that object, right? And this now allows me to deal with Newton's second law of motion. All right, so if I could go back to Newton's first law of motion a little bit, it says an object continues in a state of rest or uniform velocity unless it is acted upon by a net or resultant force. For me, this begs a question. It does not explain everything. Yes, it gives some clarity from inertia, but it does not explain. It begs a question as to what happens then when there's a net or resultant force, because it says it will stay in motion or remain at rest unless it is acted upon by a net or resultant force. So the question that it begs is, what happens then? Newton's second law answers that question. It says, when a net or resultant force is applied to an object of mass m, it accelerates the object in the direction of the net force. There is an answer right there. When a net or resultant force is applied to an object of mass m, it will do what? It will accelerate the object in the direction of the net force. So when the net force is now there, then it means the object will do what? Will accelerate in the direction of the net force. Continues further on and give us the relationship between the net force, acceleration, and the mass. It says the acceleration is directly proportional to the net or resultant force and inversely proportional to the mass of the object, telling us the relationship thereof. Mathematically, it can be represented by the formula that I spoke about at the beginning of the lesson. F net is equals to MA. The very, very important formula right there, where F net represents the sum of all forces. We are adding all the forces acting there, and the M is talking about the mass, and the mass is measured in kilograms. The forces are measured in newtons, and A talks about the acceleration, which is measured in meters per second squared. All things that we know from different places are now being brought together to form this one concept. Let's quickly talk about the relationship between acceleration and force, acceleration and mass. So it says that acceleration is directly proportional to the net resultant force. What does that mean? It means if I have a greater force, I'll have a greater acceleration. This again should to everyone should be like general knowledge. If I want to kick a ball and I only kick a ball slightly, the acceleration of the ball will be small. It will move from one place to a place that is very close to where it was kicked, right? However, if I apply a greater force in kicking this ball, what I will notice is that the ball will fly and go to a greater distance. So that shows that the acceleration was high. What caused the acceleration to be high was the higher force. So if I have high force, I will have high acceleration. The same is true, or the opposite is true. If I have low force, the force is low or small force, just kick slightly, then the acceleration of the ball will also be small. It will move a smaller distance here. If you want to kick the ball such that it travels a long distance, you have to exert a great amount of force. If you don't want to move it for a long distance, you have to exert a small amount of force. Right. Again, there is a relationship between acceleration and the mass, right? If I am kicking a ball that is very, very small, the chances are the ball that is small will move a greater distance. Let's say I kick a ball that is about 1 kilogram. A ball that is 1 kilogram can travel a large or a greater distance compared to the ball that is 5 kilograms, right? So if I kick a ball that is 5 kilograms, it's going to be difficult for it to cover a distance. Its acceleration will be small because of its mass. So if I have smaller mass, then I will have greater acceleration. But if I have greater mass, then I will have smaller acceleration. So that's what this a relationship is saying in a nutshell. Okay, so I want us to now talk about what I think or I believe is the most important part of this. Once you are able to state Newton's second law, I want you to be able to now do calculations and solve problems related to Newton's second law. And for you to do that and never fail, if you follow these following steps, I can promise you that you will never fail if you follow them and you follow them correctly. You will never fail. So these are the steps that I will use and always use to calculate any problem that I'm facing with that relates to Newton's second law. Step number 1. This is why I had to start by reminding people of free body and force diagrams, because you can never do a Newton's second law question without drawing a free body diagram. I spent time there drawing all those free body diagrams showing you. The reason is because they are going to be needed when we are dealing with this. It is important that we always start by drawing a free body diagram. Step number 2, very simple. Write the formula. F net is equals to MA. Step number 2 is very, very simple. If you make step number 1 simple as well, then step 1 and 2 become the easiest. Obvious, because it's possible to know how to draw all possible free body diagrams. Once you can see an object, you can be able to identify the forces and draw the free body diagram. And there is nothing as simple as just taking a formula from the formula sheet out again that we talked about at the beginning of the lesson. We said we are going to focus on that. It's always given it at the back of your question paper. F net is equals to MA. It's a matter of just taking it from there and writing it, and you get marks for it. So you have your free body diagram, step number 1. Step number 2, write the formula. F net is equals to MA. Then you go to step number 3. This is the most important step. This is the step that you want to master the most. Step number 3 says you must ask yourself, what is my F net for that particular scenario that you are dealing with? So you ask yourself, what is my F net? However, step number 2, much as it can be tricky, it can also be easy because the answer is already there. You already have the answer. The answer is in your free body diagram. So you ask yourself, what is my F net? And to answer that question, the answer is in the free body diagram. So you simply go back to step 1 and say, oh, here's my free body diagram, excuse me. Here's my free body diagram, and this is my answer. This is the reason why we started with the free body diagram, because we are going to encounter step number 3 where we need to understand what is our F net, and we get it from the free body diagram. Step number 4, we are going to substitute, and after substituting and finding the answer, we write our answer with units and direction. If you follow all these steps and you follow them correctly, you will always get these questions right. There will be no point where you are getting this incorrect. You start with step number 1, always, and I mean always. There will be no point where you say, I know this free body diagram, there's no need for me to draw it. You must always draw it. Step number 2, you write the formula F net is equals to MA. It's again a must, always. And step number 3, ask yourself, what is my F net? You get your answer from the free body diagram that you drew on step number 1. Then step number 4, you then work it out by substituting, working out, writing your answer with units and direction. Okay, so let's take an example and see how can we do and follow all these steps. Okay, here's an example, the example 1 there. Example 1 says, determine the acceleration of a 25 kilogram block being pulled by a force of 100 newtons and experiencing a frictional force of 10 newtons. And there's a diagram. In grade 12, most of the time, this is what is going to happen. You'll be given a question and you will also be given a diagram. It is important that you read the question thoroughly and you understand what the question is asking. And then you also look at the diagram and you compare the two. Sometimes it happens that some information is in the statement but not represented in the diagram. Right? So it's important that you read both. Don't rely only on the diagram and don't only rely only on the what? On the statement. You read the two and you compare, and then you make up your mind as to what to do moving forward. So it's important to read and read for understanding. So we are having here a question where it's asking us to determine the acceleration. We must calculate the acceleration of this 25 kilogram block. This 25 kilogram block is being pulled by a force of what? Of 100 newtons and is experiencing a frictional force of 10 newtons. So they want the acceleration. Okay? And for another person, the person will be thinking, I should just simply write A is equals to delta V over delta T, because that's what we said is acceleration earlier on. Well, yes, this is acceleration, but do you think this can help us in calculating the acceleration? The answer to the question is no. It's not going to help us. Why? We do not know the initial velocity of the block. We don't know the final velocity of the block. We don't know how long did it take to even change its velocity. So what can we do? Well, we can say a net force was applied in this object, and if the net force is applied in this object accelerated, and this is an object of mass m. So if it accelerated, then I should know that its acceleration is directly proportional to the net resultant force and is inversely proportional to the mass of the object. What am I saying? I'm talking about Newton's second law of motion. I can solve and get the acceleration of this object using Newton's second law of motion. How? By following the steps. What is that? What are the steps? Step number 1, draw the free body diagram. Always. So I start with step number 1. I draw the free body diagram. The free body diagram here starts with a dot. And then my forces. What are the forces? I have the normal force. I have the force of gravity. I have the force applied. And then I have the frictional force. Always draw arrow and label at the same time. Arrow and label at the same time. I've done step number 1. I've drawn the free body diagram. Step number 2, write the formula. F net is equals to MA. I write my formula. F net is equals to MA. Step number 3, ask yourself, what is your F net? Or ask yourself, what is my F net? So you ask yourself that question, and then the answer to that question you are going to find in the free body diagram. Okay, what is my F net? The answer to the question is on the free body diagram. Where is my free body diagram? Here it is. There is my F net, and my F net is most of the time grade 12 going to be the horizontal forces. It's 90% of the time the F net is going to be the horizontal forces for our scope, for our level. Is most of the time going to be the horizontal forces. It's only going to be vertical forces if maybe they ever talk of normal force or force of gravity. But most of the time they say calculate the acceleration, your F net is going to be in the free body diagram, and it's going to be the horizontal forces. So I go there, I say this is my F net. So it's just a matter of me taking these forces and going to add them up there, because we said F net means sum of all the forces, adding them. Here's one important thing that I must remember when I'm adding these forces. These forces are vectors. They have magnitude and direction. So whenever I go and add them up there as my F net, I must always remember to indicate their direction. Okay, so my F net is going to consist of the force applied, which is facing in a positive direction if you take to the right as positive, as I always do myself. So it's going to be F plus, adding another force, I only have F here, and I also have FF. F plus a negative FF, and this is equals to MA. You've done step number 3. Ask yourself, what is your F net? And the answer is in the free body diagram. So now it's time for step number 4. I simply need to substitute, work everything out, and write my answer with units and direction. Do I have the force applied? Yes, I do. It is 100. Minus, because plus times the negative gives us a minus. Do I have the frictional force? Yes, I do. It is 10. This is equals to 25 times A. Now I can simply solve for the acceleration, which is what the question is looking for. Then I'm going to say divide by 25, divide this whole thing by 25. That is going to cancel the 25 here, and then I'll be left with A equals 2. Then I do the calculation of 100 minus 10 over 25, or 90 over 25. This should give you your acceleration at 3.6 meters per second squared. That's my unit, and the direction would be east. It's east, or you can say the direction to the right, or you can say in the direction of motion. I'm saying east because I can see there's a diagram. There's the force pointing east. I can see the diagram is pointing to the right. However, you can also say in the direction of motion. Very, very simple steps. Step number 1, you draw the free body diagram. Step number 2, you write the formula F net is equals to MA. Step number 3, you ask yourself what is your F net, and you get your answer from the free body diagram. Step number 4, substitute, work out, write your answer with units and the direction. Let's try another example and see if we are getting this. Okay, here's example 2. Again, now they are saying determine the acceleration of 25 kilogram block being pulled at an angle. So basically it's the same block. It is now being pulled at an angle of 30 degrees above the horizontal and by a force of 100 newtons. It is still experiencing a frictional force of 10 newtons. So how do I go about doing this? Again, do not stress yourself. Just simply follow the steps. And the steps are saying the first thing I do is draw a free body diagram. I start with the free body diagram. Forces, I have the normal force, I have the force of gravity, I have the frictional force, and I have the force that is applied. Okay, what is step number 2? Step number 2 says to us we must write the formula, which is F net is equals to MA. We write the formula F net is equals to MA. Step number 3, the most important step. You ask yourself, what is my F net? The answer to the question you get from your free body diagram. And it's going to be the horizontal forces. Now, if you look at this diagram, you have a force that is acting at an angle. And we know that mathematically we cannot just add this force and this force, right? So we can't do that. We have to again, remember, jump back to grade 11 when we did component of forces. So this force here will have its component. So there's a component here that we never draw when we draw the free body diagram. We don't show this component, but it's there. We keep it in our head that it's there. That one is called Fx, the other one is called Fy. So we must remember those components, and we'll take the Fx as one of the horizontal components. Again, we are tapping back into the knowledge of grade 11. So our F net there is going to be Fx, which is positive, and we will be adding it to negative F. F is negative because it is facing in the negative direction. Remember, we're adding vectors here, they have magnitude and direction. This is equals to the mass times the acceleration. Okay, now if you remember from last year when they taught you that the components, you learned that Fx is given by the formula F cos of theta. There was all this triangle that was showing you using the trigonometric ratios, your SOHCAHTOA, how we eventually get to F cos theta, right? But it is just important that we know the formula for Fx is F cos theta. And the formula for Fy is F sine of theta, if we ever need it. So once we have Fx, we have to now expand it and write it in terms of what? F cos theta. So that's what we are going to write here in our next step. We're going to write F cos theta minus Ff, and this is equals to MA. So that's step number 3 done. And once we have done with step number 3, we're almost done, because all that is left is maths, and maths is not that difficult. Once we have covered the science part, the maths is not that difficult. Simply just see, do I have F somewhere? Yes, I do. 100. Where I see F, I put 100. Cos of, because that's an angle. Cos of, right? Of what angle? The angle is 30 degrees. So where I see theta, I put in 30 degrees. Minus, do I have FF, or frictional force, somewhere? And the answer to the question is, yes, I do. And the frictional force is 10 newtons. And this is equal to 25 times A. And then to get my answer, I don't stress about putting this into a calculator and calculating again, dragging this whole thing. I can just take a shortcut, divide by 25, because there's only one known here, and divide this whole thing by 25. I have a calculator, and the calculator can do all of this. So I take my calculator, I say a fraction sign, I say 100, and then I say cos, and I put in 30, I close the bracket, minus 10 over 25, without having to stress myself. I should find that my answer, or the acceleration, is 3.06 meters per second squared. It is also going east. Now I've written the answer with the unit and the direction. Now if you remember previously, the answer there was 3.6 meters per second squared. Now the answer is 3.06. I want you to notice something there, because this is a potential question where they will say, calculate the acceleration. And instead of saying calculating the other acceleration as I've asked you, they will actually put it in words and say, the force is now applied at an angle. And then they ask you, what is going to happen to the acceleration of the object? Is the acceleration going to increase? And they say, write down increase, decrease, or remain the same. And you ask yourself, how do these people expect me to answer this question? Well, they've just simply done what I've done there. They took the same scenario and only changed the what? The angle of the force. And as you can see by doing the two calculations, when you change the angle of the force, This changes the acceleration, and it does what? It decreases the acceleration. The acceleration has decreased, went from 3.6 meters per second squared to 3.06 meters per second squared. Now, if they ask that question, they will be asking you to explain, right? So what do you mean? Yes, you are saying the acceleration has decreased. But what has caused the acceleration? Well, you have to go back to Newton's second law to be able to answer that question. You have to think to yourself, well, there are a relationship between F net and acceleration. There's a relationship between the mass and acceleration. And one thing I can notice here is that the mass of the object has not changed. Therefore, the mass did not affect this acceleration. So only one thing has affected this acceleration, has to be the net force. The net force has decreased here. So when you apply a force at an angle, you are going to decrease the what? The net force. And if you decrease the net force according to the relationship given in Newton's second law, this is going to decrease the what? The acceleration. That's why the acceleration is decreasing then. It can also be done through calculation, where you can just simply calculate F net is equals to, and then you add these forces separately. You will find that the acceleration or the net force there has decreased compared to the previous one. I'm just trying to prepare you for types of questions that are usually asked. Okay. Right. So what I want us to do now, I want us to look at an activity from a typical exam question paper and try to see how we are expected to answer such questions. Okay. In our activity, we have a learner forgets his school bag on top of a vehicle. When the vehicle starts to move, the school bag falls off the vehicle's roof, and there's a diagram that shows all of that. There is a school bag there, then the car starts simply moving, and the car does not move with the school bag. And the question number 1 then says, which term is used to explain this resistance of an object to any change in its state of motion or rest, right? And then 2.2 is asking, use Newton's first law of motion to explain why the school bag falls off the vehicle's roof and does not move with the vehicle when the vehicle starts to move. So what I'm going to do is, I'm going to give you 4 minutes. Why 4 minutes? Because 3 minutes for answering this question and 1 minute for you to attempt this, and we are going to be back in a moment. Right, welcome back, Rachel. I hope you were able to answer these questions without any difficulty. So the question says a learner forgets his school bag on top of a vehicle. When the vehicle starts to move, the school bag falls off of the vehicle's roof. And the question is, which term is used to explain this resistance of an object to any change in the state of motion? So this question is almost asking the definition in reverse. It's trying to check whether you can define what this concept is. And the answer that is expected from you there is that you must say that it is inertia, because inertia is the property of a body to resist any change in a state of motion or rest. Then the following question asks us, use Newton's first law of motion to explain why the school bag falls off of the vehicle's roof and does not move with the vehicle when the vehicle starts to move. And the relevant answer to this could be, right, initially both the car and the bag are at rest, which is true. They are both at rest, not moving. Then the vehicle pulling away is a net force forward on the vehicle, by the way, not on the school bag. So there's a net force acting on the vehicle, but not on the school bag. The school bag will continue, according to Newton's first law of motion, in its state of rest. So it wants to continue where it is at and therefore fall off from the roof of the car or the vehicle. Okay, so here's the next question, right, that I want us to look at. But this will be looking at it together. A tow truck with a mass of 2,120 kilograms is towing a car with a mass of 900 grams. The frictional force on the tow truck is 1,000 and on the car is 350 newtons. The truck's engine is exerting a force of 8,000 newtons, right? And there's a diagram again there showing us the mass of 900 kilograms and then the mass of 2120 kilograms. And then there's a force applied of 8,000, frictional forces of 1,000 newtons and 350 newtons respectively. Question number 1 says, state Newton's first law of motion. Right, Newton's second law of motion, I mean. When a net or resultant force is applied to an object of mass m, it accelerates the object in the direction of the net force. The acceleration is directly proportional to the net or resultant force and inversely proportional to the mass of the object. Question number 2. Draw a labeled free body diagram to show all the forces acting on the car. So here's the car. They're asking us to show all the forces by drawing a free body diagram. So this should not be difficult. We go for our dot and we draw. It's 4 marks, so we're expecting to have 4 forces. All right, what is force number 1? That is normal force. Definitely it's there. What is force number 2? That is going to be the force of gravity. And what is force number 3? Force number 3 is friction. There is friction being experienced by the tires of the car on the road. And then force number 4 is going to be the tension that is provided by the tow bar that is being used to tow a car. So this is the free body diagram that we are expected to have. Okay, where with frictional force is 350 and then we don't know the tension, right? Then question number 2 or 2.5 says, calculate the acceleration of the tow truck and the car. And I want you to pay special attention as I show you how to calculate the acceleration when we have 2 objects that are connected by a string or a rope, right? So, but we're still following the rules, grade 12. We have our steps. Step number 1, draw a free body diagram. Step number 2, write F net is equals to MA. Ask yourself, what is my F net? And then substitute and get the answer, right? So what we're going to do is calculate here. The first thing that we must do is we have to separate and look at these 2 objects separately. So we have to start maybe by this one first, then work it out, then we have to go on this one. And we have to realize that if these 2 are pulling each other, they are going to have the same acceleration. That's very important to realize. And they are also going to have the same tension. These 2 things are going to help us to be able to work out this acceleration. And how do we do that? Right, what we want to do first is start by drawing a free body diagram. I'll start by a free body diagram of the car. FG, and then T, and then you're going to have FF. Then second step, we're going to write F net is equals to MA. And then third step, what is my F net? And where do I get the answer? From the free body diagram, the horizontal forces. So I'm going to say my F net is made up of what? T plus minus FF, as I've been doing, is equals to MA. Where T, I don't know, but the frictional force I know is 350. And I also know the mass to be 900 times the acceleration, right? Now, but from this point, I'm a bit stuck because I don't know the acceleration, I don't know the tension, I don't know both of these. I can't substitute one of them. So what can I do? Let me make tension the subject of the formula and say tension is equals to 900A plus 350. As I move the 350 to the other side, it becomes positive. Then let me call this equation 1 and say I'm stuck here. Let it go. Maybe I'll come back to it. Okay, from there I go and consult the track. And I say, well, the track also has forces acting on it, so I draw a free body diagram. I have normal force, I have the force of gravity, and I'm going to have force applied in this case. In the track, I'm going to have frictional force, but I'm also going to have tension from the track, right? Okay, so it's time for me to draw or write the second step, which is write the formula F net is equals to MA. Step number 3, what is my F net? Where do I get the answer? From the free body diagram, all the horizontal forces. This is force applied, all the horizontal forces. And then what are the horizontal forces? I have force applied plus a negative frictional force plus a negative tension. Tension this side was positive because it was pulling in a positive direction. Tension this side is negative because it is pulling in a negative direction. This is equals to MA. Then I substitute. I am aware that force applied is 8,000 minus the frictional force of 1,000 minus an unknown T. This is equals to 2120 A, which is the mass of the track. But then again, I'm at the similar position that I was in here, which is a stuck position, right? So with that being said, I can just simply say, okay, let this be equation 2. Then I can think again, right? I want to know what is the acceleration, but I don't know what is the tension. The same thing the other side. I want to know what is the acceleration, but I don't know what is the tension. But one thing I know is that the tension here is the same as the tension here. And the acceleration here is the same as the acceleration here. So these things are the same. So that means I can try and solve both of them simultaneously. So what I'm going to do, I'll say sub 1 into 2 mathematically. So that means I'm going to do 8,000 minus 1,000 is going to give me 7,000 minus T, which is now going to be 900A plus 350, close bracket, and this is going to be equals to 2120A. So this is going to be 7,000 minus 900A minus 350 is equals to 2120A. Then from there I collect the like terms. Then I'm going to have 7,000 minus 350 is equals to 2120A plus 900A. Right, from there, I press my calculator. 7,000 minus 350, that gives me 6,650. And then 2120 plus 900, that gives me 3020A. Then I divide by 3020 on both sides. What I will get is that the acceleration will be equals to 6,650 over 3020. My acceleration will be 2.201 meters per second squared. in the direction of motion. And that's how you solve these two questions simultaneously. Right, I'll leave you with the question of tension. You will solve the tension question, and then you'll see how far you can go by just using these two equations that we've already developed over here. That's it for me, from me, grade 12, for this lesson. Thank you. I hope you understand, or you were able to get Newton's second law of motion, and I hope you are now going to be able to solve more questions. Thank you.